Hi, my name is Nishant Bambra, and I'm a third-year medical student at McGill University. I'm proud today to be presenting my research with the Mooney Lab at St. Michael's Hospital and the University of Toronto. The name of my presentation today is Measuring Retinal Displacement via Retinal Vessel Printings and 3D Projections. In this research, we present a novel way to measure displacement using 3D projections from FAF, or fundus autofluorescence images. This presentation is a part of the larger line study from the Mooney Lab. To begin with, I believe it's important to present a quick overview of retinal detachment. In simple terms, it is the separation of the retina from the underlying retinal pigment epithelium and choroid. This separation leads to retinal ischemia, which causes degeneration of the photoreceptors responsible for transducing light into neural signals and visual processing. For this reason, rapid diagnosis and treatment is required after detachment to prevent vision loss. Two main methods currently exist for treating retinal detachment: pneumatic retinopexy and plana vitrectomy. Both are used in clinical practice at the moment, and for this reason, the Alliance study has sought to determine which of the two options leads to better visual outcomes for patients. Despite a high proportion of patients achieving anatomic success following a modern-day repair techniques, post-operatively, up to 60% of patients have retinal displacement, and many have metamorphopsia, anisoconia, decreased visual acuity, and vision-related quality of life. Randomized trials have also demonstrated that functional outcomes can vary with surgical technique in repair, with favorable results with pneumatic retinopexy in multiple trials. Post-operative retinal displacement may provide an anatomic basis for suboptimal functional outcomes following repair. For this reason, the Alliance study has sought to determine which procedure minimizes retinal displacement and maximizes visual outcomes. In the image shown here, the vessel printings can be seen with the white arrows. The RVPs represent the original location of the vessels prior to displacement, and therefore in comparing their location to the new location of matching points on the vessel, we can determine the amount and direction of retinal displacement. The Alliance study included FAFs of 157 patients, of which 83 received pneumatic retinopexy, while 74 received plana vitrectomy. Patients were recruited from St. Michael's, the Newcastle Eye Center, and the Hamilton Regional Eye Institute. In order to measure displacement, we first began by determining the location of the optic disc and fovea using a machine learning model provided by Optos. From these values, a grid shown here in black was applied to the FAF image, which provided us an ability to determine the quadrants of the points and develop an equator in later projections. Furthermore, grid squares were made in red, which allowed us to divide the image into squares of 300 by 300 pixels. This allowed us to make various measurements vertically, horizontally, and diagonally, which became incredibly useful in later 3D projections and provided us an anchoring point for future measurements. For sub-analyses, we identified a region centered on the fovea, which extended the optic disc. Within each step-size grid square, graders marked points that corresponded to matching vessel and RVP structures, which are shown here in yellow. These served as our measurement points. Determining the distance and angles between these 2 points was our primary quantitative measure. However, measuring the distance between these points on a 2D Cartesian plane limits the true measurement of the distance across the surface of the retina. For example, an analogy to this would be measuring the distance between Toronto and Tokyo on a 2D flat projection. This, if used by a pilot, would not accurately provide us the distance required to fly across the globe between these two cities. Instead, we need to determine the measurement between the two locations across the curvature of a globe or eye, like this, considering the entire flight path across the globe. For this reason, we sought to actually measure across the curvature of the retina itself stretched across the eye, rather than a 2D projection alone. This approach has not yet been done and is what makes this study novel. So to get around this, we project the image to a 3D dewarped map like this. This allowed us to measure the distance along the curvature between the RVP and vessel and between each point and the grid line fixed at the center of the optic disc. This allowed for measurements to be accurate in millimeters across the surface of the retina itself, providing a true measurement of the distances between RVP and vessel in millimeters. As you can see, the equator grid lines have also warped to the curvature of the retina. For this reason, using a 2D measurement of displacement would not provide us with accurate measurements. By marking points on the 3D projection and using machine learning tools from Optos, we were able to measure the distances of each pair of points in millimeters across this curved surface. This approach to measuring retinal displacement is novel, and we believe it will be an important technique as ultra-wide field imaging becomes more utilized in ophthalmology. In a schematic here, we show a simplified version of our pairs of points and the measurements made. By measuring the distance between the point and the RVP to the optic disc and the grid lines from it, we were able to determine the vertical, horizontal, and diagonal distances of all of our points. We're then able to determine the angle of displacement from the RVP to the vessel point, and provided us a measure of determining the aggregate direction of displacement across quadrants and grids. Here we show two examples of displacement seen in 3D projected images. Here the purple displacement we added show a displacement inferiorly, and the green displacement here shows a displacement superiorly, where the vessel is now above the RVP. Here the image is enlarged, so you can see the vessel printing and the point here a bit more. And here we provide the actual measurements and the displacement vectors. So the blue lines represent the measurement to the vessel and the red to the RVP. And yellow between them, if you can see it, is actually the measurement points between the vessel and the RVP. So for an entire image, we then summated the measurements and determined displacement throughout the image for all grid points. When looking at the data for displacement, we noticed significant differences in the number of patients that showed displacement after pneumatic retinopexy in comparison to parsed plana vitrectomy. This was significant, with a p-value of 0.001 showing that retinopexy was significantly less likely to cause displacement. Similarly, when looking at displacement within the zone 1 region centered on the fovea, with an edge point at the optic disc, retinopexy had significantly less displacement, with a p-value of 0.06. Finally, when measuring the displacement in millimeters using the 3D projection method, we found that the median zone 1 displacement was significantly lower in retinopexy patients at 0.1802 millimeters compared to 0.2324 millimeters in vitrectomy patients, with a p-value of 0.045. Furthermore, the study found a significant correlation between the patients with retinal displacement and clear functional outcomes. Among eyes with retinal displacement, there was a moderate correlation between the amplitude of maximum displacement and anisoconia, with an R value of 0.402 and a p-value of 0.003, vertical metamorphopsia scores, and BCVA. Similarly, we found that there was a moderate correlation between the amplitude of displacement in zone 1 and the following outcomes, anisoconia and BCVA. There was a weak correlation between amplitude of displacement in zone 1 and vertical morphopsia. From this data, there are strong correlations between displacement both throughout the retina and zone 1 specifically, with increased anisoconia, vertical morphopsia, and increased logmar BCVA, so reduced visual acuity, with increased displacement. So in this study, we developed a novel method to measure displacement across the retina in 3D, demonstrating that retinopexy showed reduced retinal displacement throughout the retina and in zone 1 specifically. Retinal displacement correlated significantly to reduced visual outcomes, increased anisoconia, and increased vertical morphopsia scores. Our future directions include mapping displacement of retinal vessels to vessel printing using whole vessels, and utilizing 3D projections in future measurements of retinal displacement as we continue to pursue our interest in retinal displacement and stretching in our studies. Thank you very much.